Our topic for today is the beam element. We're going to start out with classical Euler-Bernoulli theory, study that, and then learn how to develop a finite element based on that theory. Then I'm going to extend into 3 dimensions and show how that same beam can carry axial forces and torsion forces. At the end, I will review some thin-walled ideas and for torsion of open cross-section beams, but we won't hit that very hard because it's an advanced topic, and we'll mostly concentrate on what is often called the simple beam, which is the Euler-Bernoulli beam. Let's spend some time looking at classical beam theory, which for us is the Euler-Bernoulli theory. The reason is that now, as you're a practicing engineer, it might be a good time to review this theory, and some people will learn it perhaps better in the approach that we're doing, which will be based on energy rather than the older equilibrium ideas. Let's consider a straight, slender prismatic bar shown here. We'll look at the XY plane so that we're really thinking of planar bending of bars. We don't worry about axial or torsional forces at present. Those can be added in later in a linear way in our element. The bar is considered to be compact, and that is that it's either a solid bar or perhaps a square tube. Then the plane sections arguments that we're going to make will be most accurate. Let's list some of the approximations that are made in the Euler-Bernoulli beam theory. First of all, we'll require linear elastic material, and then we will restrict ourselves to infinitesimal deflections and slopes. Thirdly, we'll make the plane sections assumption, that is, that plane sections that are initially perpendicular to the beam will remain that way after deformation. And this means that you don't have any shear deformation. Beams that do have shear deformation are called Timoshenko beams, but we're not interested in that theory right now. The fourth assumption is that we will not include the z direction for any important quantities, and we won't allow stress and strain to depend on the z direction. There won't be any loading in the z direction. It will turn out with these assumptions we can study with great accuracy with compact cross-section, and the slenderness ratio should be 10:1 or greater, and the cross-sectional area should be compact, and that is close to a square, but I would be comfortable easily going out to a 2:1 ratio of height to width or width to height. An important concept in beam theory is that of how the beam, initially straight, curves into a circular arc when end moments are applied. I'll show a figure of that here. This is a segment of a beam that was initially straight. The curvature has been exaggerated so that we can show the center of the radius of curvature above. Now, the section that we're looking at carefully with the bottom length here and the top length here was originally a rectangular piece of material, which I'll sketch off to the side. And there was initially a width L0 which would have held at any elevation. After deformation, that width still holds unextended at the so-called neutral axis, which is the same as the elastic axis or the centroidal axis for this simple beam theory. And then what we might want to do is consider the strain involved in the axial direction at some arbitrary distance above the neutral axis. Let's say we measure at a distance y here, and we want this length L of y. Fortunately, both of those arc lengths are described by a common angle delta theta. And so if we want to calculate the strain, we can use the formula where we take the change in length over the initial length. Now there's a different radius of curvature for this length L of y, and it is r minus y. And therefore we can calculate the arc lengths involved. The L of y is this one, whereas the reference length is this, and then the reference length appears in the denominator. There's a lot of cancellation, fortunately. The delta thetas cancel out. The radius then in the numerator cancels out, and you're left with this simple formula that the strain is minus y over the radius of curvature. So this is the strain curvature relation that is so important to us. The radius of curvature that we've just discussed is possibly the most important parameter in the entire beam bending problem, but it's not directly measurable. So we'd like to relate that to the lateral deflection of the beam elastic axis, and I do that here. We'll measure the position of such a curve in the upward direction by the symbol V. And in differential geometry, they've shown this formula, looks rather horrible actually, where you can relate the curvature, which is 1 over the radius of curvature, to the second derivative of V, and then a modifying factor below. Now, if we restrict ourselves to small slopes, so rather than the figure I show above, we instead restrict to this figure shown below, then we can make the approximation that the dv dx term squared is much, much smaller than 1, and we can neglect that. When that happens, the 3/2 power acts only on 1, and so that disappears too, and you just get that the curvature of a slender bar being put under moments is the second derivative of the lateral deflection V with respect to x squared. Now earlier we had shown that strain was minus y over r, so now we can replace that with minus y d squared v dx squared, and this is something quite measurable. So we now concentrate our attention on the lateral deflection of the elastic axis of the bar element. At the outset, we have quite a few variables in the beam problem. Our first simplification is to assume that not much happens in the z direction, and in fact we will turn this into a plane stress problem lying in the xy plane. Let's look at a cross-section and see if we can argue some of these stress assumptions at the start. I'm looking at the cross-section of what was originally a rectangular cross-section, and then through the action of end moments has distorted somewhat, and I've exaggerated the displacements to turn this into a trapezoid. There's no loading in the z direction, and so it's rather easy to say that the stress sigma z will be 0, not only on those two free surfaces but throughout the body. And there will likewise be no shearing forces tau yz applied on these free surfaces. Neither will there be any loading on the upper surface in the shear. So the shears are pretty easy to set 0 also. So we have 2 of the 3. I'm also going to assume that sigma y is 0. Now that may seem a paradox to some of you, because the way that beams are loaded is by surface pressures on the body. But it will turn out that even if this were a loaded surface, that the load sigma y, or the traction on the surface, would be far less than the axial stress sigma x inside the body. So we're going to effectively neglect sigma y in favor of sigma x, and that turns out to be correct in retrospect. Now let's reduce our variable list further by making some geometric arguments. If we were to scribe some lines on the side of the beam, horizontal and vertical, in an orthogonal mesh, and then we put end moments on that curve the beam as shown. The plane sections argument means that these cross-sectional lines will still be perpendicular to the axis and will have right angles. But you see, that's exactly what you mean when you say that the shearing strain gamma xy is 0. So the plane sections argument is tantamount to saying that the beam locks up in shearing strain. Now it will carry shearing stress, but it is rigid in shearing strain due to the plane sections argument. Then if we look at the bottom of the beam, we can use symmetry arguments to say that those same plane sections cannot rotate with respect to each other. There shouldn't be any loading that would make them do that, nor geometric asymmetries in the beam. And so we get gamma zx is 0 also. That's two more quantities that we're setting to 0 and makes now a total of 5 variables that we're hoping will be 0 in our beam theory. Well, there's some method in the madness that we're doing here, and that is that we're trying to eliminate the terms that are going to enter into the energy statement for energy stored within the beam. We know what strain energy is. We know it comes from the various stress and strain components. If I write that out, here is the expression for strain energy density, which is the strain energy per unit volume. And it comes out to be always the product of a force-like thing and a displacement-like thing. So we have sigma x and epsilon x, and then 5 more such terms. But we have already set 3 of the stresses to be 0, and by geometric arguments 2 of the strains to be 0, and by so doing the only remaining strain energy term of any importance is that due to axial stress and axial strain. So the energy in the beam is really stored in this uniaxial manner, and a beam acts as a bundle of fibers that way. They are maintained in a relative position by the shear forces. In fact, you have locked up the body in shearing deformation so that these fibers are able to carry substantial loads acting only in axial tension. There's a story that one of the Indian chiefs back in the eastern Indian regions of the United States called his dwindling tribes together, and there were 7 associated tribes. They were being decimated by the influx of the white man and the loss of game and so on, and so he picked up a twig and broke it and said that one of us tribes acting alone snaps as easily as a twig. And then he grabbed 7 twigs and bound it with a grapevine and said, but if we all act together, then we will not break. And he showed how stiff a bundle of twigs that was. So you see, an Indian chief there may have been the first person to have come up with the real beam theory as a bundle of fibers. Or composite beams maybe, huh? Well, the bottom line is literally that the only stress-strain law that we're interested in is the axial stress related to the axial strain with Young's modulus as the coefficient relating them. So when we do the bookkeeping in a minute in our finite element, we will be very interested in this form of stress and strain. We've reviewed the classical theory, so now it's time to convert that to a finite element. We know that in terms of the Euler-Bernoulli beam, there's an underlying differential equation shown here. It's the 4th derivative of the lateral deflection. And if there are no intermediate loads in the interior of the body, then you get a 0 here. Normally that's reserved for a running load along the beam. Now we're going to consider a section of beam as if it were a single finite element. And we're going to need 4 degrees of freedom for the purposes that we mentioned earlier, namely to connect to the neighboring elements, to put information in and get information out, and then to provide the degrees of freedom for accuracy. We won't use an intermediate node in the interior of this single finite element. Very few of the commercial codes do. I think it's more likely that the user will use many elements rather than go to higher order elements here. There are various versions of beam elements in the different codes. Within the MSC Nastran code, for instance, they have what they call a beam element, which is really the more advanced element. Then they have a bar element, which is the simple Euler-Bernoulli theory. And so I think in every commercial code that you use, you must be aware of whether the element that's been developed is based on Euler-Bernoulli theory or Timoshenko theory, and then on up into higher order theories. But we'll be happy with this one. We need at least these 4 degrees of freedom at the nodes shown in our sketch, and that's adequate to carry out a consistent Euler-Bernoulli theory. Now we need to use those 4 nodal degrees of freedom and those 4 nodal forces to create a flow chart to show how we can map to the internal variables in the Euler-Bernoulli beam. As I typically do, on the right are the nodal coordinates, on the left are the nodal forces. Now in this case, force in general means either a force or a moment. These are force-like quantities. We have the internal stress field, the internal strain field, the internal displacement field. At this point, I've already taken the liberty of saying that the only important V deflection is that of the elastic axis. I'm showing here 4 generalized coordinates that we're going to define in a minute, and those will be needed to balance the 4 nodal coordinates when we use a displacement function approach. In our previous discussions on classical theory, though, we were able to show that 3 components of stress were 0 due to the peculiarity of this slender body and the fact that it's moving in a vertical plane. And then we also, through the plane sections argument, showed that these 2 strains were 0. Now the stiffness matrix that we develop is primarily a function of strain energy caused by motion of the nodes. And because we have zeroed out one or the other of all 5 of these pairs of quantities, that means that we only are left with one significant energy pair, namely the axial stress and the axial strain here. Furthermore, and I show this at the bottom of the page, we also found that the axial strain depended through the curvature relation on the second derivative of the lateral displacement of the beam's elastic axis. So that means I can get the remaining interesting energy pair by mapping solely from the lateral displacement V. And so we're going to simplify this chart and have these 4 generalized coordinates feed into the V displacement. We're going to have the V lateral displacement feed into the axial stress and strain. Now the relation, the mapping in this gap is easily filled by Hooke's law for uniaxial strain. Let's look at the simplified flow chart. Here we have still the 4 nodal displacements and the 4 nodal forces. But we've simplified in the stress-strain area. Here we show the Hooke's law that's relating axial stress and axial strain. That would be a fiber stress and strain. Here's the mapping that relates the strain to the lateral displacement, and that's basically a curvature law. We're going to introduce 4 generalized coordinates in a second, and of course then they define a phi matrix or a displacement function matrix. And lastly, there's the H matrix, which is basically a trick that relates the generalized coordinates to the nodal coordinates. Our goal, of course, is to find the overall mapping from end to end, this K stiffness matrix. Now, in this particular derivation, I'm going to start by using a displacement function rather than the shape functions, and then we'll find the shape functions later as an intermediate calculation. And the reason that we're choosing 4 generalized coordinates is to match the 4 nodal coordinates. Furthermore, because the solution, the differential equation solution to this problem, which is known a priori, would be a cubic if there were no loads distributed internally on this element between the nodes. And so this is an exact solution for an end-loaded beam element. And then it will only be approximate if you have a running load in the interior of the element. Then I can put that in a matrix form where we have our phi matrix, our displacement function, defined here. Now we need to evaluate the H matrix. This involves a trick, and that is to evaluate the internal field displacement function at the nodes. When you do that, you get a relation between the generalized coordinates and the nodal coordinates. I show that here, where we say that the lateral displacement at the left end of the beam equals the field displacement evaluated at 0, at x equals 0. Here you have, likewise, that the rotation at the left end of the beam equals the derivative, or the slope, of the field displacement evaluated at 0. At the right end, we get the same kinds of relations, that the lateral displacement at the node must equal the field displacement evaluated there, and likewise the rotations must match. We're using a logical idea here for infinitesimal displacements, that the angle theta, which is basically in radians, is the same as the first derivative, which is a slope, really. It's really a tangent value here. And that's true for the infinitesimal values that we have. So there is a small approximation buried in this, the equivalence that we've made here, but it's consistent with the basic Euler-Bernoulli theory. Now I can set those 4 equations into their proper coefficient form shown below here. And for instance, in the first equation, V at A, which is lateral deflection at the left end, means you evaluate that displacement function for x equals 0. And when you do that, the term that was once x and x squared and x cubed drop out, leaving you that VA equals Q1. Then evaluation of the other quantities gives you the same sort of pattern, and then you get this matrix H that we're interested in. I'll just present the results for the inverted H matrix. Nowadays this can be done with the symbolic mathematical programming packages such as Mathematica and Maple, and I'm finding more and more students will do that sort of thing in the classroom situation. So here's the H matrix. Now the reason that that's useful is to show the mapping then from the nodal coordinates to the internal generalized coordinates. And you can make use of that then to create the shape functions. So it's at this point that we can now use our assumed displacement function with this trick of finding the H matrix to create the shape functions themselves. And I've done that multiplication and put it here. Now these polynomials each have the character that they have a unit value at their home degree of freedom and a 0 value at the other degrees of freedom. I'll plot the 4 shape functions for you. Here they're shown on the interval 0 to L. We'll commonly use the length of the beam as the capital L. The first shape function has this unit lateral deflection, but 0 slope. Now that's kind of important to realize that there are now 2 variables per node. And so it has to have zero slope there, and then zero slope and deflection at the other end. The shape function n2 has a unit rotation, which I've taken to be 1 radian, and then it has this nice cubic function here that drops back to zero slope and zero deflection at the right end. Now I have actually scaled these shape functions on a plot package such that they're accurately scaled. However, there is a length scale involved. In other words, the rotational shape function that I've shown could be made of different size than the translational shape functions. So I give a length scale below here just to let you know that. I didn't realize that myself in teaching this material for some time. But there's an arbitrariness then in how you can normalize these quantities. But the general shapes are of interest, and you can see how the rotational and the translational shape functions have a little different character. What we've been doing is finding the components of that flow chart that we showed. Now let's continue and find the strain matrix. This is also going to help us in mapping, basically going from right to left on the flow chart. And we get the strain matrix by multiplying the strain displacement law times the shape function matrix, which we just found. The strain displacement law for the Euler-Bernoulli beam is basically a curvature relation with two derivatives on x. And the shape function was a cubic polynomial in x. So this differential operator will knock it down from a cubic to a linear function. So we can say that strain is a linear function of the x-coordinate. It also involves the y-coordinate. And of course, the strain linearly changes as you move away from the elastic axis. Well, our greatest formula in this class has been the stiffness law developed by the energy approach. And we now have the ingredients. We have the geometric law B, which is our strain. We have the material law G, which really is only the Young's modulus in our case. And if we can integrate that over the volume of the element, we'll have the stiffness matrix. Now, interestingly, the integral over the cross-sectional area, which for us are the y and z coordinates, will cough up the moment of inertia. It comes about naturally because the strain matrix B is linear in the y-coordinate. And so you end up with an integral of y squared dA over the cross-section of the beam. It comes about naturally because of our quest for finding the strain energy in the beam. The integration involved for the stiffness matrix takes several hours to work out for all the components. What I do sometimes in classroom situations, though, is to have the students develop just one term in the matrix. And then to my surprise, some of them have trouble deflating that calculation and not doing the unwanted sums, and they end up with almost the whole matrix anyway. But here's what it looks like. This is a 4x4 stiffness matrix. The terms are not dimensionally the same because you have coordinates that are not dimensionally the same. The lateral displacement and the rotation are dimensionally different. So you can see how the diagonal terms dealing with displacement have terms 12EI over L cubed, but the rotational components have a stiffness that varies as 1 over L rather than 1 over L cubed. And then the off-diagonal terms are in between. But that's all to be expected in structural problems. A second thing of interest for finite element people is the way to include distributed loads within an element's boundaries. For us, it would be line loads from node to node on the axis of the beam. And the only such loads that are kept track of are the lateral loads in the v direction. Now you might think, because there are nodal variables on rotation, that you also ought to have an equivalent nodal load for distributed moments along a beam. But I've never seen that, and I think the reason is that it's relatively difficult to apply a distributed moment along a beam's axis. And so that problem is pretty much pushed under the rug, and engineers don't seem to worry about it. It's only in the late evening when you're pondering over your notes and you realize, hey, you know, we had two variables at the nodes and only one variable in the interior. But what would keep you from making this a two-vector? And I think the only thing that keeps you from doing it is just the standard practice, that there are very few distributed moments in the world. More often there are concentrated moments, and if that were the case, then you would probably break your mesh from your beam model such that there would be a node appearing at the point where there was a concentrated moment. Now that could happen something as a large jet engine on an airplane where there was some startup or some torque applied, let's say, and maybe even some gyroscopic effects. So I imagine there are problems where there are concentrated moments routinely, and those are included in the commercial codes, but not distributed moments. And lastly then, this equivalent nodal load is embedded into the equilibrium law for your beam-like structure. And it adds in with the truly concentrated forces and moments. Let's look at a numerical example of a beam element. I'm going to treat the beam as a system by taking a single finite element Euler-Bernoulli beam and then put boundary conditions at the ends and loads on it. This is just the simplest system problem that a person could pose. And here it is. It's a finite element that's being simply supported at the two ends. In the linear theory that we're doing, such a simple support is adequate as shown. Many people would prefer to have rollers at one end to relieve any possible axial stress in the element, but our theory wouldn't create that anyway because it's an infinitesimal theory. So it's really not material whether you have two pins as shown or a pin with a roller support under it at one end. In our case, we're putting on 10 newtons per millimeter running line load here, which is a lateral load. And remember then that our answer will not be exact because the cubic that we're using for our displacement field would only be exact if this body were only end loaded. But we do have loads in interior. What we're going to try to find are the rotations at the ends of the beam because those will be the only remaining unknown deflections in the problem. If we wanted to go further in a stress sense, we would then ask for internal stresses and so on, and those could be recovered from the displacement information. I'm giving down below the material and geometric properties for this system. Our solution will involve the determination of the stiffness matrix, the equivalent nodal loads, and then the solution of the discrete set of equations. The stiffness matrix is shown here, and it's just a collection of constants that we obtain by putting those physical constants into our symbolic law for the stiffness in the xy plane. Then the equivalent nodal loads are found by integrating the shape functions transposed by the running line load. The shape function transposed becomes this matrix below. It's a cubic and then multiplied by the running load. Now I won't do that integration in detail because it's boring, but you come up with these numbers. And my claim is that it would be very hard for an individual to have anticipated that that line load would have had these, particularly these moments, these equivalent moments at the nodes. But this, the original distributed load should have much the same effect as this set of concentrated loads. And of course that's where the name equivalent nodal loads comes in. For our case, this is really crucial, because had we used lumped loads and moved that distributed line load out equally to the nodes, we would have had no displacement field at all. There wouldn't have been any moments at the nodes under the older lumped load concept. I'll sketch the equivalent nodal loads as they would appear on the beam element. Here you can see them, and notice that the lateral loads are what you would expect, because it was a 1 meter long body and had 10 newtons per millimeter, so you really had 10,000 newtons acting. And so the lateral load has followed your intuition as to what a distribution of loading should be become as it's concentrated at the nodes. But it's these moments now that are not rational. They've only been determined through an energy balance. And the idea is that for the given cubic polynomial, this is the best n moments that you can possibly choose to represent that original distributed load. So that particular set of loads is put into the equilibrium law then on the right side, and adds in with the support reactions VA and VB that are shown here. Now there are no external support moments because they're pins, so we have zeros in those locations. Likewise, I've put 0 at these two locations for the displacements at the two nodes. So we have now converted what was once a continuum problem into a discrete problem. But it is a mixed boundary value problem because we've given 2 of the displacements as knowns, and on the other hand 2 of the force fields, namely the moments, are knowns. And then we have to find the other. Our standard practice now is to separate out those equations that basically define the degrees of freedom that are constrained. So in this case, we can partition out the first and the third equations and set them aside. And it's the second and fourth equations that involve the unknown quantities that are displacement-like, which are the rotations in our problem. So we've solved for those rotations, and then that physically defines the displacement field, which I've sketched below. As an afterthought, we can find the reactions from the equations that had been set aside, and we get minus 5,000 newtons at each of the support points, as sketched here. That makes sense because we know that they had to equilibrate the 10,000 newton upward load. What we have just done is to develop the stiffness matrix and the equivalent nodal load concept in the xy plane for bending of an Euler-Bernoulli beam. Now it turns out that we really need to embed that beam into 3 dimensions so that we can do what is called a space frame. Furthermore, you really need axial force in the linear sense and torsion effects in order to do a typical frame problem. We're not going to attack the problem of buckling of those members, which involves really nonlinear axial effects. In order to embed in 3 dimensions, we need the degrees of freedom shown here. And a beam element then has 12 such degrees of freedom, 6 at each end. There are 3 translations and 3 rotations at each end. Now the beam that we just finished was for bending, or flexure it's called, in the xy plane. So the example problem we gave involved a v deflection upwards. We're now going to call that coordinate at the nodes the u2 coordinate, and the rotation that was relevant would be the u6 coordinate. At the far end of the beam, the same nodal positions would be held by u8 and u12. Now I'll gather that information for you in the next figure. Here's the newly interpreted results that we just found. that bending in the xy plane is given by a relation involving these coordinates. So what we need to do now is do the same thing in the xz plane, and it really requires a rederivation. There's a problem because the coordinate system is awkward in this case, that you find that the evaluation at a node for rotation becomes the negative of the slope. You might say that it's a little bit of a conflict between the finite element notation and the classical beam sign conventions. But it's okay, we can overcome that. It shows up as a minus sign in this relation. And it's precisely for that reason that I developed the beam element in the xy plane rather than the xz. Now some textbooks will take the xy plane, some will take the xz. Sometimes textbooks will flip the z-coordinate downward in order to avoid this problem, and then have the w deflection positive upwards. And then they don't get this paradox of coordinates here. But for us, we've got to use a consistent approach in 3 dimensions. So we resolve that by this introduction of a minus sign in these slope relations. And that turns out to cure the problem, but actually gives a different stiffness matrix. Here is this stiffness matrix in the xz plane, and it involves the coordinates 3, 5, 9, and 11. The new thing will be that there are some minus signs occurring in the interior of this stiffness matrix, and you can compare it with the one in the xy plane and see where those fall. Okay, so we've got the flexure problem pretty much in hand. Now let's look at, say, the axial tension. The linear theory we already did for the line element and found this nice pattern of in and out forces on the element. In our new coordinate system, that involves the first and the 7th coordinates with the first and the 7th forces. Development of the torsional stiffness for the beam element follows the same logic as the axial stiffness. Here I show the 2 rotational degrees of freedom at the ends, and there would be torques associated with those rotational degrees of freedom. It will turn out that you get a similar stiffness form, namely this nice ±1 pattern. And that's due to the fact that this is a statically determinate structure where the torque at one end has to be reacted by the opposite torque at the other end. The material properties are captured in the G, or the shear modulus, and then the geometric effects are captured in the cross-sectional torsional rigidity J, and then the length of the element L. The relevant coordinates, as we've mentioned, are 4 and 10. The beam element is actually one of the most complicated elements in that it exercises all 6 coordinates at each of its 2 ends, making it a 12 degree of freedom element. In addition, you have to specify the cross-sectional inertial properties, and in order to do that we need to develop element coordinates. In the Nastran series of codes, this is how it's done. There's an underlying set of coordinates called a basic set of coordinates, and then when you mention that there's a beam element in the offing, you specify the connectivity from grid A to grid B. When you do that, that automatically gives you an X element coordinate direction, which is centered at node A and pointed toward node B. Then an artificial vector V is created, and it's centered at this node A and points off into a direction specified by the user. That will define what's called plane 1, and I've shown it cross-hatched in red as the plane that passes through this vector V and the axis of the beam. you can automatically then infer that there's a plane 2 which is perpendicular to that first plane and also passes through the beam axis. So those two planes then specify orthogonal local planes, and when you specify a moment of inertia I1, that's a moment of inertia that is relevant to the beam flexure in plane 1, and then I2 is the relevant moment of inertia that deals with flexure in plane 2. It turns out that in classical mechanics, a different notation is often used, where the moments of inertia might be called IY and IZ and deal with preventing motion or flexure about the y-axis and about the z-axis, which are local element coordinates. That was the way that I learned, and I was a little suspicious of this business of using these planes, but it turns out to work very well, and now I'm pretty well converted to the Nastran way of defining moments of inertia. Let's look at the stiffness matrix for a beam element that has both torsional and axial effects included, as well as the flexure in the two planes. This becomes a 12 by 12 matrix, and notice that I'm using the convention from the Nastran series of codes with I1 and I2. The zeros are not shown here, so you can imagine them embedded in all the remaining positions. This makes kind of a nice checkered pattern here. You won't see this matrix given in many books. In fact, I've personally not seen it presented, but yet this is the three-dimensional beam element, which is possibly the most widely used stiffness matrix in all of finite elements. And notice then that you get these minus signs occurring on some of the terms, which again have to do with that coordinate conflict between the classical and the finite element coordinate systems in the XZ plane. We've completed quite a lengthy study of the Euler-Bernoulli beam, which is sometimes called the simple beam, and its conversion into an element, and the addition of axial and torsional effects, and finally the embedding into 3 dimensions. This is a rather complete study then of the simple theory. But there are advanced topics, and they're really beyond the scope of our course. I'll just mention those in this figure. For instance, when you get length to depth ratios of less than 10 in beams, you start getting into deep beam effects, where you should really consider shearing deformation. And I've sketched that here to show that this deep beam, initially a rectangle, might shear into this form here, where now you get angles that are other than 90 degrees between the cross-section and the elastic axis. The reason that this happens is that the bending stiffness, as a beam becomes thicker and thicker, varies as the depth cubed, but the shearing stiffness only varies as the depth to the first power. And therefore, relatively speaking, deep beams are able to do shearing deformation more easily than they do in slender beams. So be aware that there is a deep beam theory. Civil engineers sometimes are interested in this because some of the beams used in railroad bridges and other civil structures do become deep like this. Another category of advanced problem is when you have thin-walled bodies. Their torsional characteristics are relatively easy if it's a closed thin wall and a compact section, but as you go to open walled cross sections such as this slit tube here, you find that the torsional stiffness is really degraded. Likewise, if you have built up sheet metal structures, and the automobile industry is very interested in these thin walled open cross sections. This has led to the development of advanced beam elements such as the beam element in the Nastran series, particularly in the MSC Nastran code. So within that series of codes, it's really the bar element that is the Euler-Bernoulli beam element, and then in MSC Nastran the beam element has many of these advanced features. One that I haven't mentioned yet is that really the location of the nodes at the end of an advanced beam element is put at the line of shear centers, not the centroidal axis nor something else having to do with mass distribution, perhaps a mass axis. So even the definition of the nodes that define such an advanced beam is an interesting question in itself. Problem 1 in our problem session is that of a cantilever beam with n displacements prescribed. Here is a 1 meter long cantilever beam, and we're going to enforce a vertical displacement of 2 millimeters at the tip, as well as 1/10 radian rotation. The question is, what is the shear force generated by the wall on the beam? I've tried to make that somewhat of a physical statement. What we're really asking for is the external reaction in the vertical shear. And we want to determine what direction it is, just to make sure that we understand the sign convention. The bending stiffness of the beam is given, so we have all the physical quantities for the stiffness matrix. In solving such a problem, it's wise to block out the total size of the system and try to identify the boundary conditions. In our case, we just have one element defining our system, and it will have 4 degrees of freedom. So we know that we're going to have a 4x4 system stiffness matrix, a 4 vector of displacements, and a 4 vector of forces. This problem is particularly easy because we've been given all 4 displacements. So it's definitely in the tradition of the displacement boundary element method that you specify the displacements and that causes forces. But it is an unusual way to state a boundary value problem. Our goal is to find the force F1 at the left wall and determine its sense. You see, we're lifting up on the right end and we're rotating it, and it's not clear what sense that should be. My first guess would be that it would be a downward force trying to restrain the upward force causing this displacement U3. The solution is actually just a forward multiplication in which we can solve the first equation for F1. And when we do that, we get a total value of 57,600 newtons. Because it's positive, that means it's upward. And that's a little bit counterintuitive. However, it shows that the rotation that has been applied at this right end actually is tending to put somewhat of a downward thrust on the body and overcomes the vertical displacement. And so the reaction has to be upward, as shown. Problem 2 is an assembly of a rod and a beam element. The beam is a cantilever beam extending vertically from a rigid wall, and then the rod is connected by a pin end to the beam and extends to a wall where it also would be pinned by definition, because a rod cannot carry bending moments. The pin joint that's the common joint won't transmit bending moments from one to the other. The question is, under 1,000 Newton load at 45 degrees angle as shown, what is the horizontal deflection of that pin joint? You're given all of the material properties and geometric properties of the 2 elements, 1 meter long beam and 800 millimeter rod in length. In our solution, we'll first sketch out the required degrees of freedom for the assembly. And it turns out there are 7. We would set up the beam first of all as a cantilever beam fixed at the wall, extending upwards, and we'll take a set of local coordinates as shown. That alone requires 6 degrees of freedom. Then the rod, if we want to make life easy for us, we'll make an element coordinate system lined up to include the U5 that we've already defined, and then pick a U7 at the wall aiming in the left direction also. We know that the beam matrix would in general be a 4 by 4 matrix if we only consider flexure and we don't worry about axial and torsional stiffnesses. Ultimately, we're going to constrain all of the degrees of freedom at the wall where the cantilever beam is fixed, as well as the wall where the rod is pinned. So we will end up with a 3 by 3 problem ultimately. I'll write down the assembled stiffness matrix for this system, and here we can put in the relevant boundary conditions. I'm showing the zeros for the wall where the cantilever beam is fixed, and then the 0 in the horizontal degree of freedom at the wall for the rod. It's at those degrees of freedom that we don't know what the reaction forces are. So those are shown as F1, F2, F3, and F7. At the joint, however, we do know the external force in those degrees of freedom 4, 5, and 6, namely that there is a component of force, 707 newtons, in the horizontal and vertical direction, but there is no external moment supplied. And so we do meet our criterion that we must specify one or the other of the force or the displacement component in each degree of freedom. And you can just go down this whole list of degrees of freedom and see that that's true. At this point, we would partition out the degrees of freedom that are given as constrained. In other words, the first, second, third, and seventh equations. And that would leave us with the interior 3 equations that correspond to this matrix that I'm trying to outline here. And when we separate those out, we see that the first equation uncouples from the second and third. So we can solve 2 equations simultaneously and then solve the third one at our leisure. When we do that, we get these 2 simultaneous equations, and we can eliminate U6 since it's U5 that we're interested in, solve for it. It involves both the beam stiffness contribution and the rod stiffness contribution. Remember that those stiffnesses are conductors of force, and they both are essentially trying to restrain that horizontal motion U5 from occurring. When you solve for U5, you get the answer of 1.66 millimeters. It's positive, which was to the left in the way we set up our coordinate system. And so that's a reasonable answer. It's in the reasonable direction, and so we accept that as the correct answer. Problem 3 is a cantilever beam with a spring at the tip and then a live load in the vertical direction at the tip. This will give us some practice in studying a system with springs. Here's a figure that shows the 5,000 Newton load downward, the 10,000 Newton per millimeter spring. The beam itself is 2 meters long, and we'll pick the XY plane as the plane of interest. Then we're given the Young's modulus and the stiffness in bending using the IZZ notation as the kind of moment of inertia that opposes rotation about the z-axis. Our system has 5 degrees of freedom. That's because I'll choose to model the spring as a part of our elastic system, and we'll model both ends of the spring, including the grounded end. Now, Of those 5 degrees of freedom, 3 of them are constrained to be 0, or in other words, they are grounded. So I'll enter the zeros in these 3 locations. The beam has terms entering in its normal positions and then shows up in these locations. The spring will contribute stiffnesses in these 4 locations. After we realize that there are zeros, we understand that these columns, the first, the second, and the fifth, will vanish because they're multiplied by zeros. Also, we recognize that we can set aside the equations that correspond to those 0 displacements and set them aside to find these blue boxed reaction forces later. So then we have a set of 2 equations in 2 unknowns remaining involving the unknown displacements. Now, there's a modeling concept here which is important, and that is that when you have a spring attached to a mechanical system, that it will add a term on the main diagonal. You can, as I did, show the grounded end of the spring, but it will always cancel out of the problem. So as a result, many people are quite happy to just include the spring on the main diagonal. Another trick that people do sometimes, which I don't recommend so much, is to treat the spring as an external force and to put a force out there to be minus k times the displacement that's relevant, which in our case would be U3. That treats the spring as an external force, and then it must be later incorporated into the left side of the equation. Now let's solve the resulting 2 by 2 set of equations. Those equations are shown here with the live load acting, the 5,000 newtons downward on degree of freedom U3, and then the 0 tip moment applied. When we put in the numerical values, we come up with a matrix such as this, and then we can solve that either by elimination of variables, as we've learned in high school, or perhaps using Kramer's rule, as shown here. In Kramer's rule, it's a ratio of determinants, and what you do is substitute in the first column of the system of coefficients the live load on the right side. That will give us the solution for the first component of the unknown vector. In the denominator, you have the determinant of the full coefficient matrix. And the answer turns out to be 1/2 millimeter downward, which is a negative number. So that completes our problem session. I'd like to have another short interview here in regard to the beam element by just talking with someone that has been doing finite element modeling and analysis for some years now. His name is Peter Grimley, and he's an employee of Automated Analysis. So I went out into our working area and kind of grabbed Peter by the neck and said, Peter, we need some good input, some practical insight as to how the beam elements are used in practice today. And so I'd like to ask you something along the line of what percentage of the elements do you use that are beams, and then can you give some applications where beams have been useful to you?
As Professor Anderson said, I'm Pete Grimley from Automated Analysis Corporation. I've been working in the industry using finite element analysis techniques for approximately 3 years. I'm here to discuss a little bit some of the applications of the beam element. One of the first applications that we typically use the beam element for is in the automotive industry to simulate ribbing and other stiffeners in floor pan models. Another typical application of the beam element is in large space frames for earth-moving vehicles. For Caterpillar, for instance, uses large structural steel tubing to develop their frames for their large vehicles. The final outcome of the model is typically a plate and solid element with some beam elements included, but as an original or initial concept model, we'll build the entire structure out of beam elements with the appropriate cross-sectional properties. This helps us determine load path and potential areas of high stress where we'll need to refine our mesh in a later. A third application of the beam element that we use quite regularly at automated analysis is in the area of assembly loading or preload conditions. Typically, the beam element is used to simulate a bolt that is subjected to a known torque or axial tension load. To acquire this load, we'll use thermal loading to freeze or cool down the bolt. The reason we use the beam element in this case as opposed to the previously discussed rod element is that bending in the local area or bending in the bolt may become a concern.